Hello and welcome. And today I'm going to talk about bad encoder, which is a backdoor attack to pre-trained encoders and self-supervised learning. Now, before we know what self-supervised learning, we should know the challenge that is faced by which is faced by supervised learning. And one of the challenges it faces is that it requires a lot of labeled training data. And by a lot, I mean hundreds of thousands, even millions of training data. Now, self-supervised learning addresses this issue, and the way it does is that it works in two phases. Now, we still require a lot of data, but these data need not be labeled. We can just provide an image, or we can still provide image text pairs, but these are basically known as pre-training data set. The way it works is here. So self-supervised learning pipeline. So in the left, as you can see, these are the pre-training data set. These are basically the images. These are fed to the image encoder, which is known as F here. And this image encoder then pumps out something known as a feature vector, which is given to these classifiers, and then this classifier then classifies the feature vector, so these images, into different categories. So these are the different downstream tasks here. One of them is traffic sign recognition, one is digit classification, one is object classification. Now the first step in this self-supervised learning is pre-training an image encoder, and the self-supervised learning algorithm used in this project, in this paper, is called as SIMCLR, which is very popular. And the way it works is it takes an image and it augments it into two. So here, as you can see, this log image has been augmented into these two images, which is then fed to the image encoder, and it gives out two feature vectors corresponding to these augmented images. Now, the cosine similarity between these two feature vectors will be very large, which basically means that these two vectors are their direction is basically the same. So the algorithm says that these two are so similar, they need to be in the same bucket or the same category. Same can be said about these two cat images. Now, if we compare a cat and a dog image, so these two feature vectors, the cosine similarity will be small. So basically, the vector direction will be very different. So the algorithm will know that these two shouldn't be in the same category. These two are different, two different objects. Now, next thing is we build a classifier, and here we can see these are the traffic signs we are given as a data set. We give this to the image encoder. It produces this feature vector, and then we can label these feature vectors. We can say that if the feature vector is something like this is basically a stop sign. If the feature vector is something like this is basically a speed limit of 20 miles per hour, and so on. And after we do this, this is basically standard supervised learning, and we get a classifier which we are calling here as G. This is how it works basically. We give an image, uh, we we give an image to the give an image to the image encoder. It gives this feature vector, which is then given to the classifier. And after the classifier, it basically says it's similar to this one, so it says it's a stop sign. Uh, so there is a big problem with this is that it's very vulnerable to attacks. And one way to attack is bad encoder, which is the first backdoor attack to self-supervised learning. And the way this attack works is that, say this is the image encoder F, we can do something known as, we can add something to the images known as backdoor trigger. Now, what that means is that, let's say this trigger is something like there's a small white square in the center. This one is there's a small green square in the bottom, and so on. So we can feed these to the uh, algorithm, and we can basically get them to get different results. And the best way to see it is using this example. So here, as you can see, this is a stop sign. There's nothing wrong with this image, and it correctly predicts it to be a stop sign. This one, however, this is the same image, but we have now added this small white square in the center, and it predicts it to be a 60 mile per hour speed limit. And the issue, the way it happens is because must have provided many 60 miles per hour speed limit images to this um, model to train, and we must have added many small white squares in the center, like this exactly. So it will now create bias for this and say that because there is a small white square in the center, this has to be a 60 mile per hour speed limit, which it clearly is not. Um, so this is the threat model. So who could be the attacker? The attacker could just be the untrusty model provider. The model provider could on its own to backdoor trigger it, or it could be a malicious third party. What could be the attacker goal now? It could be the first goal is to basically get the downstream target downstream task, what the task is, and the target class pair. Then the effectiveness is one of the goal. It needs to be effective, and then the utility. Uh, Obviously, it needs to be useful to the attacker. And the last is we need to know about attacker background knowledge. So one of the attacker's background is it needs to know obviously the attack data set that it's going to attack with and the image in the target class. Now, the key idea of a bad encoder is that we formulate bad encoder as an optimization problem. So, effectiveness loss and utility loss, these are the two factors. Effectiveness loss means that the feature vector that it produces must have the feature vector must be similar to the reference images inputs should be similar to the shadow inputs, which basically means that the feature vector should be similar to the feature vector that is already being produced. And utility loss means that if it is producing a feature vector, if there's a let's say there's a stop sign, it is producing a feature vector of let's say 1 2 3. This is just an example. uh, and if we provide this feature we provide this image to test, it should still print 1 2 3. It shouldn't affect the utility of the utility loss should be less if there is no backdoor trigger to the image. Basically if it's a clean image, the utility loss should be very less, and we basically minimize the weighted sum of the two losses. um, then there is a challenge in quantifying effectiveness goal, which basically the training set classifier maintains integrity and confidentiality. And so the solution to this is again effectiveness goal, right? So we need to produce similar feature vectors for reference image and any image embedded with backdoor triggers. It needs to be similar. It shouldn't be something completely random, because then it might we might the we might get suspicious of the attacker. So this is the pre-training setup. So this is the data set that is used for this uh, project. This is available on the online basically. This is the SIMCLR is the self-supervised learning algorithm used. These are the downstream tasks, and the classifier used is a fully connected neural network. So to summarize it all, self-supervised learning is vulnerable to backdoor attacks, as we saw, and insecure encoders lead to a single point of failure in the AI ecosystem. And we basically in this project try to show that the existing defenses are insufficient to defend against bad encoder, and we need provably secure self-supervised learning algorithm to uh, actually make this self-supervised learning algorithm secure. Thank you.